question that arises here is that we are restricting our fraction of corruptions to be a constant, let's say 1 by 1000. Can you do better given that the adversary is oblivious? Can we increase the fraction of corruptions to maybe almost 1? That is, everything is corrupted except for a small number of points. Yeah. So I'm lost in different adversaries. So adversary of algorithm and try to minimize at the capital when you converge what the work. So what is the exact observation? So adversary has to corrupt the observations or the vector y in the beginning in both the algorithms, but in the earlier algorithm, adversary could see x and the noise eta and do the corruption. Here, at the beginning, you just add this vector in the beginning, and that's it. In the fully adversarial case that we were talking earlier, there the adversary has information of, let's say, x, w star, eta, everything. But in this oblivious adversary setting, adversary cannot look at x and eta. Okay, but he doesn't know the algorithm that you are using. Knows the algorithm that you are using, knows even the distribution of the data, but doesn't know the exact value of the data, and can in fact know also w star, doesn't matter. So has everything other than the data point themselves. And the corruption is in the beginning. You are given your data points as well as this vector y, and now your goal is to recover w star. This. So here all we are doing is, remember, like, we reduce this problem to solving a constraint optimization problem. You want to minimize this function which is given by this, such that this vector b is sparse. It has at most alpha times n non-zeros, right? And what we are saying is that we will try to solve this problem using a simple projected gradient descent method. In general, it's not a good idea. I will not advise it. But for this problem, we are claiming that it works out. So the algorithm is, you have some iterate bt, you do a gradient descent. This gradient descent step will take you out of your small, like sparse vector ball. So what you do is you project back onto that ball and just iterate. Yeah. Yeah. No, but the vector is still sparse, right? Because it is alpha, it has alpha times n non-zeros. So if you have, let's say, n is million and alpha is, let's say, 1 by 1000, so I will still allow you 1000 non-zeros. So it will just, so this is just the scaling thing, that as you are scaling n, we are increasing the number of outliers, but still overall it is 1 by alpha, like, it is alpha times n sparse vector only. Computation will depend on n for sure. Computation rate is n times d log 1 or epsilon. So that has to depend on n. But the final error that we are getting w star, that will go down to 0 with n. Yeah. Yeah. But it is increasing only linearly. So our computation is linear with respect to n, which is very important for machine learning problems. Any other questions? All right. So as I was saying that, can we allow more corruptions? And the answer turns out to be yes again. But for this, we need to change our hard thresholding operator. So earlier when we were thresholding, we were just looking at the top alpha and corrupted guys and took them and then made everything else 0. Now we will need to change this thresholding operator. We will say that we'll have a thresholding level tau, and every element which is below this tau level, we'll set it to be 0. If it is above this tau level, we will have it as it is. And this tau will need to be determined very carefully. I'll skip the intuition behind how we selected tau for now. I'll just go to the result. The result, what it says is that when your fraction of corruptions is 1 minus 1 by root n, then you will be able to recover w star at optimal rate. So what this means is that if every single point but root n of your points are corrupted, then you are good to go. Tau is a very dependent on each iteration. So we will need to estimate tau during each of the iteration. So it's much more careful analysis there. Then we didn't. We would have an estimate of alpha. We'll just take top alpha and guys, and that's it. No, we are getting much more, right, because no, no. Okay. So this will be a bit tricky to explain, but let me try to explain. So here, remember, we are trying to threshold this z vector, and like the main tool that we have in our hand is that the adversary is oblivious of our data points. That is, all our data points are independent and adversary is independent of it. Now, when you are thresholding your vector z at some level, then you are introducing some dependencies. And as soon as you have dependencies, then your resulting solution will start to degrade very significantly. So the way we will select tau is to ensure that these dependencies are minimized. So the idea is that you plot all these zi's onto this interval, and then you on this timeline, and then you just break this into the sub intervals, and we will find a sub interval which has the smallest number of zi's, and within that sub interval we will again do some randomization. That is, we will select a tau uniformly in this sub interval. So the intuition is that a sub interval which has the smallest number of zi's, that will not affect our next iterate too much. And on top of that, we are introducing this extra randomness, which will help more. So it's a little bit more involved, but the bottom line is, by doing this, now we can allow for fraction of corruptions to go to 1 if n goes to infinity. Okay. Now, a similar result was obtained by very interesting work by Sakonis, but using this L1 optimization technique. So rather than solving this L0 problem directly, they relaxed it to an L1 problem that has some practical issues. As I showed earlier, that those L1 optimization problems are hard to solve. In practice, they will converge very slowly to the optima. On top of that, those results require the number of points to be larger than d square at least, whereas we can get away with just d log d. Okay, so so as I showed earlier, that tau will be dependent on the z vector itself. You take your z vector, you form some sub intervals of your z vector, and then whatever interval has the smallest number of elements, you will select tau uniformly at random in that interval. So requires much more work. Yeah. Stream of information. Okay. That's a great question. Currently, these algorithms will require all your data points to be with you, and solving this problem in streaming setting is definitely very interesting. It seems very difficult that you'll be like, at least you will need to do some batching in your stream. That is, you'll need to take at least say order d points and then do something with it. It seems very unlikely that you'll be able to have memory requirement which is, let's say, constant with respect to dimensionality. That almost seems impossible. But definitely, it's an open question that suppose you can form these small batches of size order d and apply this thresholding techniques or whatever. Will you be able to solve the problem? Adversary, in that case, how it will be defined is that you assume that your data is a random permutation, and adversary can go and corrupt your data points at random locations. But adversary can, let's say, if it is fully adversarial setting, then adversary can look at all the data points and then do corruption. And if it is oblivious adversary, then the adversary cannot look at the exact data points, but it can collaborate amongst itself to figure out a corruption vector. So that's one model. But the bottom line is that you will need to have adversarial corruptions at random locations. If they are again ganging up in terms of location, it might lead to very bad answers in a streaming setting. I'm sorry. So as I said, that rather than that, I am allowing, or I am making the adversary itself to be somewhat randomized. That adversary will need to will be constrained to corrupt the data points only at random locations, at random points in your stream. Uh-huh. Yeah. Then it is the optimal, right? Like then you already have sigma root d by n. So this is, yeah. So this is the information theoretically optimal rate, whether you have outliers or not. Like you cannot hope to do any better than this. That, yeah, so that's what I'm saying, that even if you don't have outliers, you cannot estimate W star better than this rate. This is the optimal you can hope for. Yeah. So uniform scatter, but they can at least calibrate in how they are adding this B vector. So in general, for example, the type of corruptions that will happen is that one value is very large. Let's say one value is 1, and then the remaining values are very small. Say 1 by n square. So that turns out to be the hardest case in general, and that's why we needed to figure out this tau very carefully, because a fixed tau, that is if you are just taking fixed alpha and fraction and thresholding them, that technique will be fooled by such an adversary. Any other questions? All right, so as I said that, yeah, we can solve this problem optimally, but still there are several interesting problems in this space, as we discussed. Like one problem already has come up, which is that how do you solve this problem in a streaming setting? Another issue is, or another open problem is, that for the fully adaptive adversary, like the in earlier case when adversary could see everything, in that case the number of corruptions that we are allowing is say 1 by 10 or 1 by 100, but that is not optimal. Information theoretically, you should be able to work even if adversary has corrupted, let's say 50% of the points. So how do you bridge that gap? Can you come up with an efficient algorithm that can work with 50% corruptions? Then another sort of interesting direction is when the data points X themselves can be corrupted, because currently we were just corrupting the observations Y. But what if your covariates X itself is corrupted? In that case, already there is some very interesting work by Shiva Balakrishnan, Dicolo Nicholas, and Clivens et al. But there are several interesting problems in that space. So how much more time do I have? 5 minutes? All right. So in this 5 minutes, I'll just give a very high-level overview of how similar techniques can be applied to the problem of principal component analysis. So the problem is, given this bunch of data points with some outliers, how do you find the principal components? So when you write this problem mathematically, you have this data matrix X. Each column of this data matrix is your data point. Most of these data points are good. They are coming from, say, low dimensional subspace, but some of the points are outliers. So your data matrix is a low rank matrix plus a column sparse matrix. And now your goal is, given this data matrix only, can you find out this optimal subspace W star? Okay. If you apply singular value decomposition or standard PCA algorithm to it, the resulting solution is going to be very bad. You will be able to estimate your W star only up to operator norm of this error matrix. And this error matrix can be arbitrarily large. So this solution is very bad. Can you do better? Well, yes, using the thresholding ideas. So the algorithm is extremely simple, but with little bit more complication. So what you do is, given this bunch of data points, you first estimate your principal directions using standard PCA algorithm. That is, you just do SVD. The resulting direction or resulting principal component might be bad, like it might be misaligned. Now what you will do is find out all the points that are really, really far away from this line or this subspace, throw them away, which is fine. But you also throw away points which are really close to your true subspace, because they will have very large leverage on your subspace, or they will be bit too good to be true. So you throw away two good to be true points as well as very bad points, and then re-estimate your principal directions and just iterate. So again, an extremely simple algorithm, but it works well in practice as well as in theory. So this is the setting. Suppose alpha and fraction of the points are corrupted. You want to recover this R dimensional subspace. Suppose there is no noise. So either your data points are coming from this subspace exactly, or they are outliers. And suppose this matrix V, that is your right singular vectors of true data matrix, is what we call mu incoherent. This is a technical condition. It sort of says that your data points cannot gang up in some principal directions. It's just to avoid that. Under this condition, what we show is that you'll be able to recover W star exactly. Okay, and a small number of iterations. In just log 1 or epsilon iterations or log 1 or zeta iterations, you will be able to estimate your true subspace exactly. And note that in each iteration, you are just doing PCA. So the algorithm is essentially standard PCA, but run for a small number of iterations. Okay, and the fraction of corruptions that we are allowing is something like 1 by mu square r. Mu is the incoherence condition that I told you earlier, or the constant for that condition, and r is the rank of your subspace. And interestingly, this is information theoretically optimal up to constants. So you cannot hope to have any better than this fraction of corruptions. Okay. There was a similar result proposed given by Huanshu, Constant Karamanis, and Sujay Sangvi, but their result will require an algorithm that runs in time order n square d. So it is quadratic in the number of points, which is prohibitive for machine learning applications. Our algorithm runs in time order PCA, and PCA typically runs in time which is linear in n as well as d. So our algorithm is a linear time algorithm. Okay. Now you can have several bells and whistles on top of it. What if you have noisy data? We can say something. What if your data, your noise is Gaussian? We can say something, but I'll ignore all of this. Let me just show you that this also works in practice. So we applied it to this malicious URL detection task. So the task was given a bunch of URLs, find out the anomalous or malicious URLs. And a simple approach to do that is you take your URLs, embed them in some vector space using TF-IDF embedding. Then you do PCA on your data points. The anomalies, the intuition is that the anomalies or the malicious URL will lie really far away from your principal subspace. Okay. So when we applied this our robust PCA algorithm on this data set, we observed that our accuracies are much better than applying standard PCA, right? That is, if you just do PCA with all your training data, which will have malicious URLs also, then the resulting subspace can deviate quite a bit and your accuracies might go down. But using this algorithm, you will be able to solve the problem optimally. Another sort of interesting thing here is that because we have the ground truth, that is, we know that what URLs are correct and which URLs are wrong. So what we can also do is just take this correct set of URLs, run PCA on them. So that's clean PCA, and look at the accuracy. And here what we observe is that our robust PCA algorithm is able to match the accuracy of that algorithm. So that algorithm has this extra information that what are really good URLs and what are bad URLs. So that's the best you could hope for using that technique. And what we observe is that we are still able to match that. Okay. So in summary, learning with outliers is really critical. Any machine learning system you take, you will have outliers. And what we are here sort of proponing is a very simple approach which is based on thresholding. This technique is not increasing your running time significantly because it is at the core of it, it is still using your standard optimization tool. But what we show is that for a variety of problems, you can obtain strong theoretical results. For future directions, there are several of them. So one is that, for arbitrary functions, can we come up with a more general theory rather than solving this problem for each individual scenario? Another sort of thing is for deep networks, as I mentioned earlier, it seems like that they already are robust to these outliers. Can we sort of show that? And then for individual problems like robust PCA, there are some open questions. All right, so I'll finish with this slide. At Microsoft Research, we are looking to hire very good people at all levels. So send me email if you're interested. Sorry, can you come again? Okay. If we can form the basis vectors for them, then yes, it should be possible. But yeah, we have not tried it again. All right, thank you. Sorry. Yeah, painting is a fairly popular application for such line of work. Who? Suhas Tigali from